Electric machines come in two types: radial flux and axial flux. Radial flux machines have been widely used for over a century, while axial flux machines, though relatively new, are experiencing a growing demand, especially in the automotive sector. Axial motors offer several advantages over conventional motors: high power density, efficiency and lower heat generation, design and installation flexibility, improved cooling and ventilation, which is advantageous in high-demand applications. Axial flux motors find applications in several industries. Automotive industry, increasingly used in electric vehicles, such as cars, buses, and high-performance sports vehicles. Aerospace and aviation, used in electric propulsion systems for aircraft, drones, and other aerial vehicles. Renewable energy sector, employed in wind turbines and hydroelectric generators due to their ability to generate high torque at low speeds. Industrial automation, utilized in applications like conveyor systems, robotic arms, and precision control mechanisms, leveraging their compact size and high torque. Despite their advantages, axial flux motors face several challenges and limitations: heat dissipation, manufacturing complexity, high-speed operation, control and drive electronics. Designing control and drive electronics capable of managing unique characteristics, like skewing of windings and high pole counts, is a significant technical challenge. Recent advancements in research in axial flux motor technology include nanocomposite magnet materials, high-temperature superconducting (HTS) windings, advanced computational modeling and simulation, leveraging advanced algorithms to analyze motor behavior under diverse operating conditions, leading to more robust and efficient motor designs through rapid prototyping and iteration. Now to the design and analysis of the axial flux motor using EMWORKS software. At this point, my colleague will lead the discussion.
Welcome again. We shall show you how to use EMS and SolidWorks to simulate an axial flux permanent magnet machine having a 24 poles double-sided rotors. Since EMS is an add-in to SolidWorks, the #1 3D CAD software, the creation and modification of the geometry is as easy as a pie. We shall give you a quick overview on how to create an EMS study and link it to a SolidWorks motion study. Then, we will analyze the results from several studies that have different materials or other input parameters. Before creating a SolidWorks motion study, make sure to activate the motion add-in as shown. Click OK. To create a motion study, right-click below the motion area as shown and choose Create a new motion study. Click on the motors icon and choose Rotary Motor. Select the face of the rotor as shown. Under Motion, choose Constant Speed and enter 500 RPM. Click OK. Enter 0.05 seconds for the end time of simulation and zoom to fit. Click Play to pre-review the motion. Motion study is complete and ready to be coupled to EMS. To add a new EMS study, right-click on the project name and choose Transient Magnetic. Click on the Coupling Analysis tab and check Motion Coupling. At this point we are ready to couple the EMS study to the SolidWorks motion study. Under Motion Coupling, choose the desired SolidWorks motion study. Selected the moving components, which are the rotors and the magnets. Under Band component, choose the band, which is the air surrounding the moving parts from all sides. Please refer to EMS help to learn more about the band. Click OK. That's it, and that's all it takes to couple an EMS study to SolidWorks motion. Let's apply the material for each body. The stator is coreless. The material for the outer air, inner air and band is air. The coils are obviously made up of copper. The material for the magnets is N4212. The material for the rotors is mild steel. The magnets have a strength and direction. To set the direction, right-click on a magnet part and choose coercivity direction. Choose the Y direction. Click OK. Alternate the coercivity direction between +Y and Y for neighboring magnets. To add a coil, right-click on the coil's icon and choose Wound Coil. In selected entities, choose the bodies that make up the coil. Under Entry Port, select an interface. Under Exit Port, click Same as Entry Port. Click on General Properties tab and enter 15 for AWG and 180 for the number of turns. Click on the Current Source tab and choose Sinusoidal Current Source. Type 0 for DF, 50 for frequency, 30 for IA, 0 for IO, and -0.004 for TD. Click OK. Repeat the same procedure for the other two coils. All input variables are the same except for the time delay TD. It should be -0.010666666 for coil 2 and -0.017333333 for coil 3. All the pre-processing is now complete, and we are ready to run the transient magnetic study coupled to motion. Right-click on the study name and choose Run. Solving will take around 15 minutes on a laptop since it is a transient study coupled to motion. Let's instead examine existing studies that were run previously. We have the results for 8 studies. Studies 1 to 3 are on load current driven analyzes with a rotor speed of 500 rpm and a frequency of 50 Hz using different magnet materials. Neodymium, ceramic, and samarium magnets are used in studies 1, 2 and 3 respectively. We will demonstrate the effect of the magnets on the output torque. Study 4 is no load analysis with neodymium magnets. Study 5 is an on-load voltage-driven analysis with an additional coupling to circuits. Study 6 is an on-load current-driven analysis with an additional coupling to steady-state thermal and core loss function in the rotors. Studies 7 and 8 are again on-load current-driven analyses. The speed of the rotor is 1000 rpm for Study 7 and 500 rpm for Study 8. The effect of the speed on the eddy loss will be demonstrated. Let's examine the results of Study 1 in some details and then compare the results among the studies later. After the run is complete, Results folder is created and contains different type of results. Double-click on Results table to examine lump circuit and mechanical quantities as well as motion results, including force, torque, back EMF, resistance, inductance, flux linkage, current, and energy for each time step or each motion position. All of the results table quantities are plottable as function of time or position. For example, click on the TY torque component and click Add in the parameters field. Click on Pop-up Plot. The plot of TY versus time appears. You can track it, smooth it, print it and export it. You may equally view the listing by clicking on its icon as shown, which you can save in different formats. Follow the same steps to plot any of the table quantities. For example, let's plot the back EMF or the induced voltage for all the coils. To plot the motion parameters, click Plot at the bottom of the table as shown. It shows the angular displacement of the moving bodies as function of time. You may also plot the velocity and acceleration. To close the results table, click Close. The magnetic flux density and magnetic field folders contain the near flux density and magnetic fields in the entire model. From the magnetic flux density folder, we can create different types of plots: fringe, vector, streamline and 2D plot. Right-click on the magnetic flux density folder and choose 3D fringe plot, no clipping. The magnitude of the magnetic flux density is color-coded, where the red color is the maximum and the blue color is the minimum, as shown on the legend on the right side of the plot. Click on different time step. The values change. Click OK. Right-click on the plot icon and animate. To conclude, EMS coupled to SolidWorks Motion and Electric Circuits offers you one-stop design platform where you can look at all design aspects of an axial flux machine in one single integrated environment. The results presented are just few from a plethora of valuable design parameters that can guide you in optimizing your axial flux machine and other electric machines. Thank you for attending this